Yeah, thank you. Good morning, everybody. So yesterday we stopped right in the middle of a proof. Maybe not the best thing to do, but let me try to repeat where we are and what we still need to do. So we were about to prove this characterization, which problems can be solved easily if you perturb the input. We proved one direction of this characterization already, and the second one is where we stopped. And basically what we are trying to prove now is, assume we have a problem that we can solve in pseudo-polynomial or pseudo-linear time by some algorithm A pseudo. And we are talking about problems that were in this form of linear binary optimization problems. So I have basically a binary set of feasible solutions, and I want to optimize the linear objective function over the set. Let's say I can do that in pseudo-polynomial time. Then what we are about to prove now is that if we can do that in the worst case, then we can solve the problem in polynomial time if you perturb the coefficients of the linear objective function. So this implies polynomial smooth complexity. And we started already with the proof, and actually we did most of it already. And the idea, as I told you, is rather simple. So we know that we can solve instances in which all the numbers are small integers. Now we get an instance in which all the numbers are basically continuous random variables. And now what we're trying to do is we simply round all the numbers so that they become small. And then we use the pseudo-polynomial time algorithm to solve the rounded instance. And we know that in classical worst-case analysis, this very often gives good approximation algorithms. But now, what we are claiming is that it even gives you the optimal solution with high probability. And the main tool that we are going to use is this winner gap that we defined yesterday, and that we actually also analyzed yesterday. And we defined it simply as the distance between the second best and the best solution. So let's say C is our objective function that we want to minimize. X star is the best solution, X double star is the second best solution. And then we say delta is just the difference. How much better is the best solution compared to the second best? And in the worst case, this can be arbitrarily small. In fact, it can be 0 if you have two optimal solutions. But what we proved yesterday is the probability that delta is at most epsilon is bounded from above by 2 times n times phi times epsilon. So, or to put it differently, with high probability, there's an inverse polynomial gap between the best and the second best solution, which, at least for me, is a bit surprising, since the average distance of two solutions is just exponentially small. But for some reasons, the best solution is very well separated from all the other solutions. And based on that, we can draw the following conclusion. So let's say I round all the numbers in the objective function the following way. So maybe before I state the lemma, let me give a small definition. So this is lemma and definition. So when I say I get a coefficient ci from my objective function, and I round it down, and I write an index b, then what I mean is that I essentially round it down after b bits after the binary point. So we scaled the numbers all such that they're between -1 and 1. So the important question is, how many bits do they have after the binary point? And when I write a b, then I mean there are b bits. And similarly, if I round up with an index b, then I mean that basically I leave b bits after the binary point. Okay? Yeah, so for example, if Ci is positive, then rounding it down after b bits simply means you truncate all the bits after the bth bit. Okay, and now I do such a rounding, and I want to know what is the probability that the optimal solution does not change by this rounding. And for that, let me denote by, so for some objective function a, let me denote by opt of a the optimal solution with respect to this objective function. So opt a is simply the solution with minimum objective value, with respect to a among all feasible solutions from the given set S of feasible solutions. And now I claim the following. The probability that there exists a vector C prime, which is defined as follows. For every component of Ci, of C prime, we have that it's either Ci rounded down or Ci rounded up. Yeah, so C prime is just a rounded version of C, and every component is either rounded down or rounded up. And the probability that there exists such a vector C prime, such that the optimal solution with respect to C prime does not coincide with the optimal solution with respect to C. So this is the bad event that we don't want to have, that the optimal solution changes. And the probability that it happens is at most well, maybe I can integrate the proof already in this. So when can the optimal solution change? How can I relate this to this quantity of the winner gap? Well, so what happens? When I round after b bits, then I change the value of my number by at most 2 to the minus b. So that means when I have a solution, the value of this solution can change by at most n times 2 to the minus b. Since it contains at most n of these coefficients, each is changed by at most 2 to the minus b. So the value of any solution changes by at most n times 2 to the minus b. And that means if my winner gap, or the optimal solution can only change if my winner gap is at most 2 times n to the n times 2 to the minus b. Since the optimal solution changes by at most this, the second best also changes by at most this. So if the distance between them is larger than twice this, then the optimal solution cannot change, right? So we had the same argument yesterday at some point already. So now I can just plug in the bound that we have proven. So this is now our epsilon. So we should get something like n squared times phi times 2 to the minus b plus 2 probably. Okay, so, and this, as I mentioned yesterday, gives us immediately an algorithm that has worst case polynomial running time, but a certain failure probability. So you could now, for example, do the following. You could say set b to, say we set it to the logarithm of n cubed phi plus 2. And then we use this algorithm a pseudo to compute the optimal solution where we round down every coefficient after these many bits. So we compute opt C rounded down. And by this notation, I mean that I take any coefficient from C and I round it down after B bits. And I can do that in time. Yeah, well, what is the running time? We talked about that yesterday as well. So we are assuming that A is pseudo-linear. So it has some polynomial running time in the input length times a linear running time in the largest coefficient. And we said already yesterday, if all the numbers can be represented by B bits, then if I scale them so that they are integer, they are bounded by 2 to the B. So essentially my running time is 2 to the K times 2 to the B. And since we have chosen B logarithmically in the number of variables and phi, what we get is, well, n to the K times n cubed phi. Now you can argue that the input size, capital N, is at least the number of variables. And this way, what we get is a polynomial running time in the input size and this perturbation parameter phi, even in the worst case. Yeah, so we just do the rounding, we compute the optimal rounded solution, and I've chosen B in such a way that the failure probability is at most 1 over n. So with probability at least 1 minus 1 over n, this gives the optimal solution. Okay, so that's great. That's already a very severe indication that the problem is not too hard. But as I said, actually, we want to do it the other way around. So we want to have an algorithm that has expected polynomial running time, but always gives the correct output. So somehow we have to get the randomness into the running time. And yesterday I mentioned already the idea how we can do that, but we have to look at that carefully. So the main idea is as follows. We do this for some B, maybe for this one, or you can even start with B equals 1. Then you compute this optimal solution, and then you try to detect whether or not it is the optimal solution with respect to C. And if it is, then okay, clearly you have found the optimal solution. If not, you increase the precision. You take one more bit into account and you repeat this process. And you do this until you have found the optimal solution. And now, of course, the main question is, how do we detect if the solution we get here is optimal with respect to C? I mean, this doesn't seem to be an easy problem since, I mean, if you could solve that, then, I mean, it seems like we could solve the problem anyway. But there is a very nice sufficient condition for this solution to be optimal. And before I tell you how that looks like, let me first of all write down what I just said in pseudocode. So I call this algorithm adaptive rounding. And adaptive rounding does the following. Simply says, okay, for B equals 1 to n, do the following. Compute the optimal solution with respect to the coefficients rounded down. Then we call the magic subroutine that tells us if this solution is optimal or not. Let's call this solution X. We call the subroutine certify. And certify gets the solution X and the number of bits that we have used. And certify tells us whether or not X is optimal. And if that's the case, okay, great, we're done. We just return X. And if this doesn't happen until n, then in the end we solve the problem by brute force, which hopefully won't happen too often. Okay, so the main question is, how can we implement this certify? And the trick is to solve basically this rounded instance again, but with slightly differently rounded coefficients. So basically, here I rounded every coefficient down. And now I will round down some of the coefficients, and I will round up some of the other coefficients. So, and to make this precise, I will specify a set of coefficients which I denote by C tilde. And I set C tilde I to be either Ci rounded down or Ci rounded up. And which of these cases I use depends on the value of x. So, and the idea is somehow that this should be the rounding that is worst for x. So the worst rounding for x, by which I mean the following. Let's say we want to minimize C, and x has at some position I a 0 entry. Then, in that case, I will probably round down, because I make this coefficient smaller by rounding down, but the solution x basically doesn't get better since it doesn't use it. And if x uses position I, if xi equals 1, I round up, since that makes the solution worse. It can make other solutions worse as well, but it definitely makes x worse. And in this way, this is the most unfavorable rounding for the solution x. And now the only thing I do is I compute the optimal solution with respect to this objective function. And of course, I do this again by using this algorithm A pseudo. I can do that again in the same running time, since I haven't changed the precision. Yeah, I'm still using only b bits, but now some are rounded up, others are rounded down. And now I simply return if x and y are equal. So I return true if x equals y. I return false if x is not equal to y. And I claim that whenever this certify method returns true, then x is really the correct optimal solution. Okay. So why is that? The argument is pretty simple. So let's say we are in this situation. Certify returns true. Then, okay, we know that x is by definition of the adaptive rounding procedure the optimal solution with respect to the coefficients rounded down. But since certify returns true, it's also the optimal solution with respect to the coefficient C tilde. And now assume that it's not optimal with respect to C. So assume that this a solution Z such that Z is better than X. And yeah, we want to derive a contradiction based on this assumption. So, and actually what we now look at, so what is the value of Z with respect to C tilde? And I claim that for all I, we have that Ci times Zi is at most, Ci tilde times Zi is at most Ci tilde times Xi. And if this is true, so this is something we still have to prove, but let's say this is true, then it implies, of course, that C tilde Z is at most C tilde x. Oh, sorry. Let's maybe first of all prove that. So sorry about that. So let's say, okay, there are actually two cases that are relevant. The first case is that zi equals 0 and xi equals 1. So if zi equals xi, then this is trivially satisfied. So we only need to look into the cases where they are different. And now I guess I will even show something stronger. So sorry about that. I will look at the difference between these values. And I will argue that the difference between these values very sorry about this. It's the other direction. So I care basically about this direction. And I claim that this is always at least CIXI minus CIZI. So that's the claim that we're going to prove. And okay, let's consider this case. So what is Ci tilde xi minus this? Well, if xi equals 1, then we just said that we round Ci up. So this is Ci rounded up times xi minus, well, zi is 0 anyway, so it doesn't matter what the coefficient is, so I can simply change it to Ci. And this is, of course, at least CIXI minus CIZI. Okay, great. So in that case, we definitely have this inequality. And we also have it in the second case. Again, using the definition. So xi is 0, so I can again, without changing anything, replace zi tilde to ci. And now this is ci rounded down. And again, this is at least ci xi minus ci zi. Okay? And now that we have this condition for every I, we can conclude that C tilde x minus C tilde z is at least C x minus C z. We assumed that z is better than x, so this is strictly positive, and so this implies that the solution z is also strictly better than the solution x with respect to C tilde. And in that case, our algorithm certify would return false, since x is not optimal with respect to C tilde. So if we assume that it returns true, then this is a contradiction, and this concludes the proof. Okay? So this certify really works in the correct way. It gives us a sufficient condition for x being optimal. So now we have definitely an algorithm that always gives us the correct output. Now the only thing that remains is to analyze its running time. So let's say t is a random variable that denotes the running time of this adaptive rounding procedure. Then basically the crucial question is what is the final value of b when I leave adaptive rounding? I mean, how many iterations of this for loop do I actually make before I have found the optimal solution? And let's say this is a random variable that we call x. So let's say x equals the final value of b yeah, in the adaptive rounding procedure. So when do I leave in the third line adaptive rounding by returning the correct optimal solution? And now the only thing that remains is to analyze essentially this. And let me introduce one more notation. I will denote by Tj the running time of the jth iteration of this for loop. And now Tj is not a random variable. Tj is just some fixed number. And we can express it as follows. Well, what happens in the jth iteration? Well, essentially, what I do is I make two calls to this algorithm ape pseudo. I make one call directly in line 2 of adaptive rounding, and I make another call in the certified procedure. And everything else can be neglected. So these are the most costly parts of the algorithm. So I make two calls to this ape pseudo algorithm, and the calls are in such a way that all the numbers can be specified by d bits. So using what we have said before, have I written it down somewhere? Maybe not, but anyway, the running time of this will be n to the k times 2 to the j, right? Since this is the running time of this pseudo-linear algorithm, it's polynomial in the input size, and basically linear in the largest number, and the largest number will be 2 to the j in the jth iteration of this for loop. Okay? And now I can say, well, what is the expected running time of this algorithm? Well, just sum over all values that x can take, say from 1 to n. And we sum the running time of iteration j multiplied with the probability that iteration j is actually executed, so that x is at least j, plus the running time for line 4, for the brute force. And I'm cheating here a little bit. I assume that I can do this brute force solution in time 2 to the n. So it might be 2 to the n times some polynomial. I mean, I can even write it like that. But maybe strictly one should add that as an additional assumption to the theorem that you can solve your problem by brute force in exponential time. So, but okay, this is of course very bad. It's exponential, but it happens only with small probability. So it can only happen if x is at least n. Okay, so the only thing that remains is to basically analyze this term. And that's not too hard. So let's simply plug in everything we know already. So we have just argued that Tj is O of n to the k times 2 to the j. Well, we also know what this probability is, because, well, this follows from this lemma that we've stated here. So the probability that j bits are not enough is n squared times phi times 2 to the minus j plus 2. Since here we argued that basically, yeah, this is exactly this event. So if this does not happen, if for any kind of rounding the optimal solution stays the same, then we're done, right? Since then certify will return true. So the failure probability is this. Or to put it very carefully, I reach the jth iteration if the j minus first iteration failed. So that's why I actually have to plug in the probability that iteration j minus 1 fails, and so basically I have to plug in for b j minus 1. Okay, and then I have this term here. And again, I only reach this term, well, if the iteration before, if iteration n minus 1 fails, so I plug in the according bound we have. Okay? So is that the idea is clear? And then, okay, you just have to look at these terms carefully, and then you see a couple of nice things. First of all, you see that this exponential part cancels out. So here we have 2 to the j in the running time, but the probability that we reach the jth iteration also decreases exponentially with j. So this exponential part cancels out very nicely, and this implies that, well, if you look at the sum, well, there are, sorry, this should be a small n. So I have n terms in the sum, and every term can be bounded by n to the k. So the exponential part cancels out. So what remains is only n squared phi. And here also the exponential part cancels out. So what remains is just a polynomial. And again, using that the input size is at least small n, we can probably write this as simply polynomial in n and phi. And that's what we were heading for. So our expected running time is polynomial in the input size and this perturbation parameter phi. And we will always get the correct output. Okay, any questions about this? Okay, I have one. Where did we use that our algorithm is pseudolinear? Why was that important? Well, it was important in the very last calculation, since what would have happened if, say, the running time would be pseudo-quadratic? Then instead of 2 to the j here, we would have had something like 2 to the 2j, right? And then this wouldn't have canceled out. So this way, we have really used essentially that the algorithm is pseudolinear. It's not strictly necessary. You can get around that, but then the analysis becomes much more technical. So that's why I didn't want to present it here. The idea is still somewhat the same, but you have to work much harder to get the same statement if you have only a pseudo-polynomial algorithm that is not pseudolinear. Then a couple of remarks about possible extensions. So actually, you might wonder, why did we only perturb the objective function? I mean, you can also think about perturbing the constraints, like we actually did for the knapsack problem. There, what we, in our original analysis, perturbed were the weights, so the constraint. And actually, you can also do that. So pretty much the same analysis also goes through if you look at problems of the following type. So let's say you want to maximize or minimize some arbitrary objective function. And now the feasible solutions for x are given again by some set S. That is a subset of 0, 1 to the n. And now let's say you are given additional to this constraint, one or even multiple linear constraints. So you could think, for example, about there are problems like you have a constrained shortest path problem. So you have a graph, you have weights and edge lengths, and you want to find the shortest path, but only among those paths whose weights does not exceed a given budget. And you can formulate such problems in this setting. And now I just wanted to point out that the same statement is actually true for these kinds of problems. And the statement here would be, you can solve this problem in expected polynomial time, or it has polynomial smooth complexity, if and only if there exists a pseudo-polynomial algorithm in the coefficients of the constraint. And this even works if you have multiple linear constraints. So in that sense, this is pretty general. And there, by the way, I mean, the idea is roughly the same, but you have to be a bit more careful with the details. I mean, here, basically what I said before was if you perturb or if you slightly round the coefficients in the objective function, what you will get, even in the worst case, is a good approximation to the optimal solution. This is not the case here anymore, since rounding, at least if you do it in the wrong way, can actually make infeasible solutions feasible and vice versa. So you have to take care that this doesn't harm the analysis. But the main idea is very similar. Actually, surprisingly, there's not only this winner gap that separates the best from the second best solution, but one can also argue that in such settings, actually, the best solution has a significant distance from the constraint, so it doesn't become infeasible by the rounding. And say all solutions that are better than the optimal solution, but are cut off by this constraint, also have a significant distance from W, which means they do not become feasible by the rounding. So also there you have a very nice and very surprising separation, similar as for the winner gap. Okay, are there any questions about this part of the lecture? If not, I will now finally admit that I'm a computer scientist and show you some slides. So let's see if I'm able to do that. Okay. Oh yeah, perfect. Not yet, but. So okay, these are actually the slides that I meant to show you in my first lecture, but you see we talked about all this already, and now what I would like to talk about is linear programming. I mean, linear programming is actually the problem for which smooth analysis started. And yeah, I have some pictures here on these slides that I wouldn't be able to draw by hand. That's why I decided to do that part on slides. So okay, I guess after this week, I don't need to tell you what a linear program is. You should have seen that quite some time. Maybe just about my notation. My objective function will be C, as usual. Constraints are denoted by A, the coefficients, and yeah. So that's, and N will be the number of variables. Then, okay, we don't need to talk about that. You know that LPs can be solved in polynomial time, but what you very often use in applications is the simplex method. So very simple algorithm. I guess you have seen that before as well. So you look at your polytope of feasible solutions. You start at some arbitrary vertex, and then basically do local search. So if there is a better vertex in the neighborhood, you go there, and you do this until you have reached a local optimum, which by convexity is also a global optimum. So one thing about this description is that, of course, you have a bit of flexibility when there are multiple better solutions in the neighborhood. And this is determined, or which solution you take is determined by the so-called pivot rule. So basically, like in this situation, you could either go to that solution or to that one, and which one you take is determined by this rule. And there are multiple such pivot rules that have been analyzed and suggested. Simply do it at random, take steepest descent. Or there's something that is called shadow vertex pivot rule. And let me first of all introduce what that means. It's actually a very nice geometric pivot rule for the simplex method. And it works as follows. So assume you're given some feasible vertex of your polytope. Let's call it x0. And the first thing you do is you compute an objective function for which this given vertex is optimal. So it's actually the other way around as you actually want to do it. Actually, you're given the objective function c and you want to optimize it, but now you're given the vertex and you find the optimal objective function for that given vertex. And let's call that u. And then you have two objective functions. You have the objective function u that you just computed, and you have the objective function c that you actually want to optimize. So two objective functions, and let's assume they are not linearly dependent. That's not too interesting special case. So let's assume they span a two-dimensional plane. And then what you do is you take this polytope and you project it onto the plane that is spanned by these two objective functions. Yeah, so you just take the shadow of this polytope. And the shadow of this polytope has a couple of very nice and useful properties. I mean, first of all, it's a polygon. I mean, it's not necessarily closed, but let's not deal with that case. So let's say it's a polygon, so it's some closed polygon here. I mean, you can also do it if it's an open polygon, but for the point of illustration, it's better to think about a closed one here. Then, two very crucial properties are the following. The projections of x0 and the projection of x star, which is the optimal solution, are both also vertices or nodes of this polygon. This is not true for any vertex of the polytope here. So for example, if you take maybe this one here or that one, they are projected to the inside. But this does not happen for these solutions x0 and x star. And this is, of course, due to the choice of these objective functions. So they are definitely mapped to vertices of the polygon. And additionally, every edge that you see in the polygon corresponds to an edge on the polytope. So any edge here is also an edge in the high-dimensional polytope. And this gives rise to the following pivot rule for the simplex method. So you start at x0, and now you basically simply follow the edges of the polygon. Yeah, so in this case, there's actually a minor mistake here. When we want to maximize C, I would go actually this way, but anyway. So let's say we go this way, doesn't really matter, there are just two choices in the polygon. Then what I get is a sequence of edges of the polygon, and by these properties, this translates into a path on the polytope. So that is the shadow vertex method, for this, the pivot rule for the simplex method. Yes?
So, I mean, you don't actually project, right?
Yes, it's true. Of course, you don't compute the projection completely, and then you run this algorithm that basically you compute the projection on the fly. Yeah, so whenever you at some point you compute what will be the next step in this polygon, and you can compute that on the fly, of course, without computing the whole projection in advance. Okay. Then, okay, what do we know? So theoreticians have analyzed the shadow vertex rule, and they have found examples where it requires an exponential number of steps. So it's, for me, always hard to imagine, since I cannot really think in high-dimensional geometry, but you can come up with some polytopes whose shadow has an exponential number of edges here. So, and it's in fact not that hard to come up with these examples. So which means in the worst case, your algorithm requires an exponential number of steps to find the optimal solution. And yeah, of course, we know this for almost any other known rule for the simplex method. So so basically, from a theoretical worst case point of view, this seems pretty much hopeless. But in practice, Simplex method is still quite fast. So I mean, sometimes if you look into these experimental papers, you find statements like it usually requires O of m steps. I mean, this might depend on the LP you have, but sometimes you see statements like that. In any case, it seems very fast. So much faster than these worst case results predict. And of course, it's also clearly faster usual than ellipsoid method, which is a polynomial time algorithm. So here we have this discrepancy between theory and practice, and we try to explain this by smoothed analysis. And basically, I guess we can almost skip these slides since I've told you all that before. So of course, the reason also here is that classical theory is just based on worst case LPs, but these are not the LPs we actually care about. So I guess we have talked about that before in the context of the knapsack problem. So let me directly come to the probabilistic input model in this case, which is slightly different from what we analyzed for the knapsack problem and for these linear binary problems. So what we will do for LPs is the following model. So we have an adversary, and the adversary can essentially choose an arbitrary LP. Yeah, an arbitrary objective function and arbitrary constraints subject to the normalization constraint that the norm of all these vectors is 1, which is, first of all, just a normalization, so it's without loss of generality. And then, if we only had this first step and we would analyze the running time on such LPs, this would be worst case analysis. But now, we add some randomness to our inputs, as we did in case of the knapsack problem. I mean, there we said that the profits or the weight cannot be specified exactly, but you have a certain amount of randomness in them. And the same is here. So we say that we take this LP given to us by the adversary, and we add some random noise to it. And we do it in the following way. We take simply each coefficient from this constraint matrix, and we add some Gaussian to it. Yeah, and this Gaussian, this normal distribution, will have standard deviation sigma and mean 0, which means basically we just have some Gaussian noise on all the coefficients in the constraint matrix. And now you see we have this parameter sigma, which measures the standard deviation, and you can see that's very much as this parameter phi that we had before. Actually, you should think of sigma being 1 over phi. So for phi, it was the case, the larger phi is, the more powerful is the adversary. Here it's the other way around. So the smaller the standard deviation, the less randomness we have, so the more powerful is the adversary. So again, we have this parameter that measures kind of the strength of the adversary. So if the standard deviation goes to 0, we have a worst case analysis. If it becomes very large, we have some kind of average case analysis. And now what we want to find is we want to find a bound on the expected running time in terms of the input size and this parameter sigma. Yeah, and the smooth running time is, as before, the worst expected running time the adversary can achieve. So basically, we want to prove for any choice the adversary can make, the expected running time is polynomial in the input size and this parameter 1 over sigma. Yeah, this is formally defined here in this slide. So let's say LP n comma m denotes the set of all LPs with n variables and m constraints. For a given LP I denote by T of I the running time of my algorithm on that instance. And then the smooth running time is defined as, yeah, we take the worst LP the adversary can specify. And then we look at the expected running time when we take the LP I and perturb it. So that's how this is meant to be. Yeah? So the adversary makes the worst case decision. He takes the worst LP. And then we look at what happens if we slightly perturb it. And then we look at the expected running time. And this is, by the way, of course, not clear and usually not the case that the adversary would choose the same input that he would choose in a classical worst case analysis. So it might be the case that actually the real worst case input for classical analysis is quite fragile when I perturb it, but there might be a different instance which is only slightly better, but which is more robust against perturbations. So that's why, yeah, this is usually different. Okay, why do we consider this model? I guess we've talked about that also. I mean, basically, in the first step where we have this adversary, we want to allow the adversary to specify the overall structure of the LP. So we don't want to look at completely random LPs because they are not that realistic either, but we want to have the adversary to give us a certain unknown structure of the input. And then we simply want to add a small amount of random noise in the second step. And if you can prove that this smooth running time is small, say polynomial, then it proves at least that worst case instances are rather fragile. So as soon as you have random noise, you're very unlikely to see such a bad exponential example. And yeah, now what is the smooth running time of the simplex algorithm, or more specifically of the shadow vertex rule? And this question has been brought up by Dan Spearman and Xianghua Tang, who also invented this framework of smooth analysis. And yeah, in 2001, they proved the following lemma, which is kind of the main ingredient in their analysis. So they showed when you have an LP that is created, as I told you, by which I mean where the coefficients are subject to random Gaussian noise. Then, and you take this LP, or you take the polytope that it defines, and you project it to some fixed plane. Then, the expected number of edges that this projection will have is polynomially bounded in the size of the LP, in the number of variables, the number of constraints, and 1 over sigma. Yeah? And this is kind of what we want to, because in some sense, this shows that the number of steps that the shadow vertex method can make is polynomially bounded in expectation. Well, I mean, I think the proof of this had like 30 pages in their paper, but that was not enough, since I didn't talk about some details so far. I mean, basically, they concluded with another 30 pages this theorem out of that. And the theorem is really what I just stated, that the smooth running time of the simplex algorithm with the shadow vertex pivot rule is polynomially bounded in n, m, and 1 over sigma. So even if, so when I have some small perturbations, it's unlikely to see exponential examples. And a couple of things that I didn't tell you and that make it very different to go actually from this lemma to that theorem are the following. I mean, first of all, I didn't tell you at all how we find the initial feasible solution x0. I mean, of course, there are multiple ways to do that. There are these two-phase simplex methods. But the issue with these is that in the first phase, you don't have Gaussian distributions on the coefficients. So you introduce some additional constraints, but definitely you don't have this nice property that all the coefficients are Gaussian. And then the second problem that looks like a technicality, but is really difficult to handle actually, is the problem that once I found my solution x0, the plane onto which I project a polytope is, of course, depends on x0, and x0 depends on the LP, of course, which means that the plane onto which I project the polytope is actually not a fixed plane, but it's a plane that is somewhat correlated with the matrix A. So there's some correlation between the, so this random x0 kind of, and the, or basically between the plane and the polytope. Yeah, and that makes it really hard to get from here to there. But okay, so Dan Spearman and Xianghua Tang managed to do so, and they proved this nice theorem. And in their paper, I mean, it was nice to have this theorem, but it was also maybe even nicer to introduce this notion of smooth analysis, since this triggered a lot of work in that area. Let me mention one improvement of this, which is due to Roman Vershinin, who a couple of years later proved the following remarkably result. So he proved that the smoothed running time of the simplex method with the shadow vertex rule is actually polynomially bounded in n, in log m, and 1 over sigma. So m is the number of constraints. So basically, the number of steps we make is even only polylogarithmic in the number of constraints. And yeah, his result is also nice because the proof is much shorter and much cleaner. And it gives way better exponents. So one thing I didn't tell you, so you should always get suspicious if somebody just writes poly, right? The exponents are like 96 or so. So it's not quite practical, but here they are at least, I think, single-digit numbers. So yes.
So just going back to back one slide.
Uh-huh.
In your first lemma, like it's not enough to have just this lemma, even assuming those differences, right? Because when you go to the new point and you're recalculating the view, you're going to get a different plane.
Oh, no, you don't recompute the plane, actually. So, I mean, you could, of course, say I go to the next point, I compute another U, and I reproject, but I don't do that. So I stick to my initial projection, so the one for x0. So, I mean, it would be a valid and correct algorithm to do, basically, to reproject it, but you don't have to do that. You can stick with the original projection.
So, I mean, I guess in the smooth analysis, this is okay, but it could be in the, if you didn't perturb it, multiple points land on the same vertex, right? And then how would you choose?
Okay, yeah. So in fact, degeneracy is in that setting an issue, yeah. So you're right, it doesn't happen in perturbed inputs, but you're definitely right that in general, if you have degeneracy, then you have to be a bit more careful with that, yeah. Actually, to prove this theorem, Roman-Verschinen, first of all, he changed phase 1 to get rid of these dependencies. And actually what he did is he took the given LP and he added a vertex in a random direction. And then he took that vertex as a starting point. And well, basically, if you add a vertex in random direction, then with constant probability, it does not change the optimal solution. And this way, he could somewhat get rid of these dependencies. And I mean, it's maybe not a good idea to take a proof of 30 pages and to boil it down to one statement here. Yes.
I mean, this theorem looks like the algorithm would not even read the input. Does the input explain them?
Oh, you mean? Oh, yes, but okay. Actually, I do not talk about the running time here. I talk about the number of steps of iterations. I mean, if you do an iteration, of course, you have to read the input. Yeah, that's true. Yeah. Okay, and maybe to give you just one extremely high-level proof idea how you analyze such things. So what Roman-Verschinen did was actually the following. Basically, he proved that in such a projection, if you look at the angles between consecutive vertices, so basically, yeah, so you have here these rays that go to the vertices, and you look at the angles between them. Then he was able to prove that these angles are not too small with high probability. And from that, he was able to conclude that there cannot be too many vertices on this projection. And yeah, he had a very nice and clever argument for that. And that is, yeah, say one very high-level idea of his proof. Maybe, so this is everything I wanted to tell you about the simplex method, but maybe I can tell you a couple of very interesting open questions related to this. I mean, first of all, the probably obvious question would be, can we analyze different pivot rules? It would be really great if we could, but so far, I think nobody really has a clue how to do that. I mean, this shadow vertex rule has this very nice geometric interpretation. So somehow everything boils down to bounding the number of vertices on such a projection. And for other pivot rules, we usually don't have such a nice geometric property. And that's why, so far, it seems very hard to extend these results to other pivot rules. Something that would be even more ambitious would be to try to prove, say, the polynomial Hirsch conjecture for random or perturbed polytopes. I mean, it could very well be the case that if you do this perturbation, you have between, or the diameter of the polytope is polynomially bounded in these terms. So that could very well be the case, but yeah, we don't know. So these are, I think, very interesting, but probably also very hard questions in that area. Another question that often arises is a question about the model. So this is actually something we very briefly discussed already yesterday. Namely, if you do these perturbations, then essentially every number will be unequal to 0. And very often, the zeros in your constraint matrix encode some kind of structure of your problem, and you don't want to perturb them. And so an interesting question would be, can you handle so-called zero-preserving perturbations? These are perturbations where the adversary can choose for any number to either say, well, this is a perturbed number with, say, some Gaussian distribution, or a phi perturbed number, or I deterministically set it to 0. So, and I think it would be very interesting to see whether such an analysis can also be done for these zero-preserving perturbations. We know, by the way, for the analysis of Pareto-optimal solutions, also if you have multiple perturbed objective functions, then zero-preserving perturbations can be handled. So there, we really studied that explicitly, and we could show that even if you allow zero-preserving perturbations, you get polynomial bounds on the number of Pareto-optimal solutions. But for the simplex method, this is not known. And I think it would be very interesting if one could make some progress in that direction. So if there are no more questions about that, then let me see. Yeah, maybe I can conclude. Okay, I'm not going to talk about the TSP anymore today, but let me give you some final overview of known results in this area of smooth analysis. So a couple of these things I've covered in the lectures, but obviously not all of them. So what is known about linear programming? There's not only a smooth analysis of the simplex method, also other algorithms have been analyzed, like interior point methods and the perceptron algorithm. And essentially, yeah, so the results go in the same direction. So for example, for interior point method, the result, I mean, we know that interior point method is polynomial, but the polynomial gets better if you assume some perturbation. Then we've seen these results about combinatorial optimization problems. What I haven't shown you are results for local search. Actually, there are quite a few results out there about the running time of local search algorithms. So since, take for example the TSP, a very common heuristic for the TSP is to do some local search. And I think the most basic version is 2-opt, which essentially means you start with an arbitrary tour, and you take 2 edges, remove them from the tour, and replace them by 2 other edges, so that you again get a tour that is shorter than the initial one. And you do this until you find a local optimum in which such an improvement is not possible anymore. And very often these local search heuristics have exponential worst-case running time. And very often you look at these examples that prove this exponential worst-case running time, and you're pretty sure this example will occur nowhere. I mean, they are very well crafted to show this exponential running time, but in practice, these algorithms are usually very fast. And there are some results on this. So basically, for this 2-opt algorithm, we were able to prove that its smooth running time is polynomial. Then there's also some work in machine learning. So there's analysis of clustering algorithms like k-means. That's also a local search algorithm that works very well for clustering. And they're basically, oh, sorry, forget about this. I should have deleted that. So that's, I used these slides before, and there was another talk at 2. I guess that's not going to happen today. Anyway, so I think machine learning is also a very nice area where smooth analysis can be applied, since if you talk with people in machine learning, they have all kinds of heuristics that seem to work rather well, but usually they are very bad in the worst case. There's some work on scheduling algorithms, about the quality of scheduling algorithms, and multi-objective optimization we have already covered here. And there's also work on, let's say, classical algorithms like quicksort, binary search trees, and Gaussian eliminations. So basically, also for these algorithms, you can show in some sense that the running time improves, so the problems get easier if you assume that your input is to some extent random or randomly perturbed. Okay, I think that's the end of this overview. Are there any questions? Well, if that's not the case, let me do a little bit of advertisement. So I didn't ask the organizers if I'm allowed to do that, but I hope it's okay. So if you don't have plans for next week, Thursday and Friday, there will be a workshop in Aachen about, you see, efficient algorithms in game theory, optimization, and data science. So I think we have a nice set of invited speakers. So Jochen is one of them, and we also have some contributed talks. So if you're interested to come there, just send me an email, and I hope this will be a very interesting workshop. Okay, thank you.
Thank you, Heiko, for these fabulous lectures. Any questions? I have one. So you talked about you characterize some class of problems that have polynomial smooth complexity. Is there anything known for harder problems? So when there's a problem that has is conjectured to have exponential time complexity, when does it drop below?
Yeah, good question. I don't know. I haven't seen anything like that. So, I mean, so far we didn't go beyond NP hardness. But yeah, it's definitely a valid question, and there might be results like that problems that are exponential time hard or somewhere in the polynomial hierarchy, that they might get easier if you're perturbed. That's, I think, might be very realistic. Yeah.
Other questions?
Yeah. In the Brazilian algorithm that you showed earlier, the dependence on the number of constraints got to log n.
Yeah.
Is there any kind of condition you could impose, like some form of separation orphan, where you had an exponential number of constraints in the LP, and you could still solve it in polynomial time smooth analysis?
Yeah, that's a good question. I don't actually know if that would work. I mean, since you have to be careful about the way how you perturb. So at least I haven't seen anything like that.
It's hard to imagine how you would improve Gaussian elimination by perturbation, because it's already in cube.
Okay, I have to admit. Yeah, I have to admit I should look into that paper again. I thought that exactly that was proven. That I mean, probably it's. I mean, it depends probably on the model you use. I mean, if you use the real RAM, then you might not be able to improve. But so the question is probably about encoding length of the intermediate solutions. But okay, I should definitely look into that paper again before I tell too much that is recorded. So.
More questions? If not, then let's thank the speakers again.